continuity equation. It is based on law of conservation of mass, which states that mass flow rate through a system should be constant. In this video we're going to talk about continuity equation, and we're going to derive continuity equation in rectangular Cartesian form in three-dimensional space. Now in Cartesian form, the conservation of mass principle can be stated as net mass flow is constant. That means change in mass should be zero. And we are going to prove it for three-dimensional Cartesian space. Let's take an example. These are the coordinate axes x, y and z, and let's assume a small element in the flow. Let's suppose m dot x is the mass flowing into the cube along x direction, and the mass flowing out of the element in the x direction should be m dot x plus some change in that mass, and the change we can write it as m dot x plus dou by dou x m dot x times dx. The dimensions for the element should be dx, dy and dz. So this dou by dou x m dot x is for small infinitesimal length, and for the length of dx it should be multiplied by dx. The mass flow rate can be given as density times area times velocity, and mass, as you know from the definition of density, density is mass divided by volume, so mass will be density multiplied by volume. Let u be the velocity in x direction, v velocity in y direction and w velocity in z direction. And ax, area in x direction, it is the area through which the flow is flowing along x axis. So it is in this case dy dz. Ay is the area along which the flow in y direction is flowing, which is here, and which can be given as dx dz. And similarly in z direction we have this area through which the flow along z axis is flowing, and that is dx dy. And the volume of the element can be taken as dx dy dz. Now mass flow rate along x direction is rho times area in x direction times velocity in the x direction, which is u, and which is equal to rho dy dz u, because ax is nothing but dy dz. Similarly, mass flow rate in y direction is rho times ay times v, velocity in y direction, which is equal to rho dx dz times v. And mass flow rate in z direction will be rho, the density, multiplied by area in z direction multiplied by velocity in z direction, which is w, which is equal to rho dx dy times w. And mass is nothing but density times volume, so we have here density rho times dx dy dz. Now we can apply the conservation of mass principle to over this element. So we can write the change in mass in x direction, the change in mass in y direction and the change in mass in z direction, and change in mass along the time, that means the control volume change. The time rate of change should be equal to 0. So this is our main equation, that is known as continuity equation. So for this particular example we need to find the values and put those in this equation. In x direction we have change in mass along x direction should be given as mass coming out of the element in x direction minus mass coming in the x direction. So it is m dot x plus dou by dou x m dot x dx, which is mass out, minus m dot x, which is mass in. This m dot x gets cancelled out. We get dm dot x equals to dou by dou x rho dy dz times u, because m dot x, as we know, rho dy dz u times dx. And here dy dz are the dimensions of the element, which are constant, which can be taken out of the derivative. So if you take that out, what becomes is change in mass in x direction dm dot x equals to dou by dou x of rho u times volume, because dx dy dz is volume. So this expression we get for x direction. Similarly, for y and z direction we can have dm dot y equals to dou by dou y rho v times volume, and for z direction dm dot z equals to dou by dou z of rho w times volume. Also in control volume, the time rate change of mass can be written as dmt, and that is dou by dou t of mass, which is dou by dou t of rho times volume. And if you put these values in the equation that we have stated from conservation of mass, we get this: dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w plus dou rho by dou t equals to 0, as all the terms contains volume term which is constant and which can be cancelled out. And this what we get is continuity equation in three-dimensional Cartesian form. Now, if flow is incompressible, that is density is constant, so we get the simplified form as dou u by dou x plus dou v by dou y plus dou w by dou z equals to 0. This is an important form because in fluid mechanics we generally treat fluid to be incompressible, except in few places where we solve compressible flows. And this is continuity equation. Thank you.